Okay, do a few problems with me to get ready for the rationals test. So a rational number means that it can be written as a fraction. So look at all of these fractions. And at the beginning here on this first problem, I'm going to just note it that the denominators are the same. That makes it really easy. So the way I'd like to do this is to have you try this problem. Take a minute, write it down, give it a shot, and then hit pause. And then when you're done, hit resume, and I'll show you how it should have gone. All right, so I think you're back from having hit pause. If you didn't actually hit pause, go hit pause. Do the problem. Listening to me, you're going to remember 10% of this. Doing it, you'll get up to like 70% of it. All right, so here we go. These have a common denominator, so then I can just add the tops. The denominator is already set. It is x plus 3. And the top, I can add this plus, oh, that's the easy kind. I don't have to worry about distributing that negative. See, if it was a negative, I'd have to watch out for that. All right, so I can just add like terms, and the x and the 3x makes 4x. And the 1 and the negative 5 makes negative 4. There we go. All right, here's another one. Way harder. Looks kind of similar, but it's way harder because, number one, it's a subtract problem. So we got to worry about that negative up there and how to do that right. And you have to get a common denominator. So you multiply by the other denominator, which is, in this case, x minus 1. You always do the same thing on the top and the bottom because then effectively you just multiplied it by 1 in a creative way because x minus 1 over x minus 1 is just 1. All right, and now to get the common denominator, I got to multiply this by something, and I multiply it by the other denominator, which is x. Now I'm going to go put in some what are called implied parentheses. Those are really important. You should know that they're there. They're implied. Okay, so now we look and make sure we did it right before we even proceed. Is that the same as that? Yep, so we have a common denominator, and it is x times x minus 1. Now you could multiply that out, but I think it's better to just leave it alone because at the end of the problem, I would have said, if you can factor it, you should. Okay, next, that's 2x goes with negative 3x. Now, if you don't get what I'm doing with this negative, what I'm really doing is I'm changing the problem and putting this negative on the 3. It's like I multiplied the 3 by negative 1, okay? And now that 3 can distribute to both parts. Now you know that I couldn't have another minus here, or I'd have a negative, and that makes positive, right? So it has to be only one negative here. So I moved it there, and now I'm going to multiply it there and there. And this is what's really important and really easy to mess up. So now I had 2x over here, and I put that with the negative 3x that I'll get for this first part. And that makes negative x. And then my negative 3 times the negative 1 makes positive 3. And there we go. Since this is already factored, I'd be able to see if there's anything that would cancel. And no, you can't cancel those x's, like the one on the top and the one on the bottom, because the one on the top is part of an add problem. It is not factored out. All right, so there's my final answer. And that covers add and subtract of fractions. Now here's multiply and divide. See, I'm going to start with a divide problem, and then I hope you know that I'm going to change it to a multiply problem, and I'm going to flip this thing over. So the 3x goes on the bottom, and the 2x plus 18 goes on the top. But did you get a sense of like, wait, you should factor that? Because you're right. All right, so that 2x plus 18, do you get there's a 2 in both of them? And that factors out. And then I could divide this by 2 and divide this by 2, and I'd have x plus 9. Okay, so I just factored it. Now that's important because then you can see what things will cancel. All right, I'm just going to rewrite it down here just to make it all nice and neat. Okay. Now, as you could imagine, I'm going to factor this side. There's an x in both of those. X comes out to the front. And what's left? x plus 1. Now I have a x for this bottom part here, the x squared minus 81. I have that little pattern memorized. But even if you didn't, you could go, well, I'd have to have an x and an x to make the x squared, right? And then since the last number of my problem is negative, I'd have to have a plus and a minus here. And then 9 times 9 makes 81. So, and then if you multiplied that all out, you realize it actually does exactly equal x squared minus 81. All right, now a bunch of things can cancel. Not everything, but a bunch of things. So I see this x plus 9 and this x plus 9, and most people see those. But did you also see that there's an x here and an x here? Those are both part of multiply problems. They can both be canceled. What does that leave on top? The 2 times the x plus 1, and on the bottom, the 3 times the x minus 9. Now don't multiply those out, because at the end I would just say, if you can factor it, you should. So you should leave them factored like that. So your answer on this one has a 2 on the top with an x plus 1 and a 3 on the bottom with an x minus 9. And there you go. I know that doesn't look super simple, but that is a typical difficult divide problem, which turned into a multiply problem, so it kind of covers both multiply and divide kind. All right, and then there's graphing. So on the graphing kind, I'm not going to make a great big graph first. First thing I'm going to do is figure out the horizontal and vertical asymptotes. If you can just remember that this bottom one is where the vertical comes from, and I bet you'll remember that we don't trust the inside stuff here. Those implied parentheses go in, and I'm like, oh yeah, I'm not going to say x equals negative 1. I'm going to say x equals 1 is the vertical asymptote. And then by logic, you'll be able to say, well, this other one must be the horizontal asymptote. And the horizontal asymptote is 4, but I can't say x equals 4. That wouldn't make any sense. I've already done an x equals 1. I need a y equals 1. And I trust the stuff on the outside. Now, another thing we could have asked you about this is, which way did the parent function move? Like if you had graphed the parent function, which just a quick sketch would look kind of like that. I kind of messed that up. I'm going to try that again. There. And with these key points, then if I was asked where did this thing move, I would say it moved to the right one. Because see, this asymptote that used to be right on the y-axis, it's going to move over to the right one. And that makes sense, doesn't it? Because our vertical asymptote's going to be at x equals 1. And the whole thing moves up 4. That means this dotted line down here, the asymptote that was at 0, the horizontal asymptote, that guy, it's being moved up 4. So if they had just asked you what the transformations were, you'd say it moved right 1 and up 4. If there had been a negative in the problem, that it introduces what's called a reflection. And that's if it's on the outside there, it's a vertical reflection. All right, but we didn't have one of those. So. Okay, so to actually finish the graph here, I have done my asymptotes, and I'm now going to put them on the graph. The x equals 1 goes right through x equals 1. Okay, that was that one. And now the y equals 4. That goes up 4 spots, and there's an asymptote there. Now, these normally start with a spot here and a spot here, and then we draw the little swooshes, as I call them, in there, and they get closer and closer to the asymptote. Same with this. Okay, and now this is a really important part. You should really take a second and make an XY chart and see if the point you picked here is actually working. Okay, so if I had graph paper, you can trust me that this would be at 2, 5 right there, 2, 5. This point right here. And I'm going to make sure that 2, 5 really works, because if it doesn't, then I didn't do it right. Okay, this 2 goes here, And now I have, and the 5 goes here. And then we see if it really works. 1 over 2 minus 1 is 1. So 1 over 1 is 1. 1 plus 4 is 5. It worked. Sweet. Now I know I did it right. This other point right here, if you were on graph paper, you'd be able to see, since this line right here is at y equals 4, then we're just underneath it, so that would be at 0, 3. And if I put in a 0 right here, do I really get 3? Let's find out. 1 over negative 1 is negative 1. Negative 1 plus 4 is 3. It's worked. Sweet. Okay. So these can be tricky. There's a lot to know about the graphs. But remember that thing where if I had put a negative in the front of the problem, I'm going to put one in green here and just say, what if there was a negative here? How would that change everything? It would change it a lot. The points would be different. The asymptotes wouldn't change a bit, but the points would be here and here. And then my graph would look like this. And then you still, again, should check those points. And you'd check this point, you'd put it on your table over here, and you'd realize it works if there's a negative right there, because that is a reflection of the graph. So again, I know we didn't have that. I'm just trying to prepare you. You have to know how to handle the reflected graphs. And they just basically move from where the blue lines were to where the green lines are. All right, there's some practice for today. I hope this helps, and we'll have the test when you come back on Thursday.